Hello again, folks. Let's look at homework set number 22. We have two problems from chapter 7 that are very similar to each other. And then we have a problem in our new chapter on momentum that is pretty easy because we're starting that topic. Let's start out with problem 20. In this problem, we have a 5 kilogram block that is being lowered a distance of 4 meters. And so it's going to be down here. And during that time, we have a rope pulling on the block with a force of 45 newtons. Now, if you do a free body diagram of the block, you know that a 5 kilogram block is going to have a weight force of 50 newtons. And this tension force by the rope of 45 newtons is not going to balance that. And so that diagram screams down. And so this thing is going to speed up in the downward direction. Since it's moving down and the acceleration is down, it will be speeding up. In this problem, we're asked first to find the Werk done by the rope. Well, you remember that Werk had a very interesting definition. It was plus the force times the distance if those two were in the same direction. It was minus force times the distance if those were in opposite directions. And it was 0 if those were perpendicular to each other. Well, in this case, I have a tension force that's up and a displacement that is down. And so that's going to be negative Werk. And it's going to be, the Werk is going to be negative the force, 45 newtons, times the distance of 4 meters. And that's going to be negative 180 joules. Now, during that time, the change in gravitational energy is just going to be the mass times g times the change in height. Well, the mass is 5 kilograms, and g is always 10 newtons for each kilogram. And the height, if I'm going from up here to down there, that's going to be a change in elevation of negative 4 meters. And that's going to give me a change in potential energy of negative 200 joules. And you would expect a negative change in the gravitational potential energy. Gravitational potential energy gets smaller as you get closer to the center of the Earth. And if something's getting smaller, its change is negative. If your bank account is getting smaller, well, you'd think of that as a negative change, okay? Now, the last part is the part that kind of trips people up, and that is, what's a change in kinetic energy? Well, I don't know how fast this was moving before the rope started pulling. I don't know what its initial kinetic energy was. I could assume that it started from rest, but that's not always a safe assumption. That's not always the way things start when a problem starts. So let's look at something that's really an important tool to have in your toolbox. Normally, we always use the grand high Werk energy equation this way. The energy in the morning is equal to the energy at night, except when it's not. And it's not when there's external Werk done. Werk done by an external agent. In this case, the external agent is the rope, okay? Now, this is the most useful form of this equation, but it's not always the right tool to use. Okay, that's the one you'll use most often. But every now and again, you'll find a case where you don't know what the initial energy is, you don't know what the final energy is, and all you really want to know is, well, what's the change? So I can rewrite this by subtracting off the initial energy from both sides. If I do that, this equation becomes Werk external is equal to energy final minus energy initial. Well, anytime you have a final minus initial, that's the change. My final weight after this this lockdown is over, minus my initial weight, will be what happened to me during the lockdown, okay? Now, because that change can happen in two different buckets in this problem, it can happen in the kinetic energy bucket or the gravitational bucket, or both, I can rewrite this as Werk external is equal to the change in kinetic energy plus the change in gravitational energy. Well, that's convenient because I'm looking for this, and I know the other two. We said that the Werk was negative 180 joules, and I said that the change in gravitational energy was minus 200 joules. Okay? So if you've got two bank accounts, and this bank account went down by $200, but your total worth only went down by $180, that means this bank account must have gone up by $20. So that's going to give me a change in kinetic energy of a positive 20 joules. And that's what we expected. We expected this thing to speed up because it was moving and accelerating in the same direction. And sure enough, it did. The change in kinetic energy is positive. That means it was speeding up. Okay? So that's that problem. Let's look at the next problem. I don't have to erase this top part because, like I said, this second problem is very similar to the first one, and it's going to be using the same idea. In this case, we have a ramp and wouldn't you know it, the angle of that ramp is 37 degrees. Who could have expected that? And we have this block, in this case it's a 10 kilogram block, and it's being pulled up this ramp with a tension force by the rope on the block, and that tension force is given in the problem to be 55 newtons. And we're told that during that pull, the block moves a total distance of 5 meters up the ramp, so that a little bit later it's going to be up here. Okay? So 5 meters would go Okay, again, part A of this problem is asking for the total external Verk. That Verk, this time the pull is up the ramp and the motion is up the ramp. So now it's going to be positive force times the distance. That's going to be positive 55. The force in this case was the tension by the rope on the block. That's going to be 55 newtons times 5 meters, or plus 275 joules. Now, part B again is find the change in gravitational energy. Well, again, that's just mg times the change in height. Well, that's going to be 10 kilograms times 10 newtons for each kilogram. And now we need to find the change in height. Well, because of this 3, 4, 5 triangle, if we travel 5 meters up the ramp, that's the same as moving to the right 4 meters and up 3 meters, okay? That's a 3, 4, 5 triangle. That's why we use 37 degrees. Now, the change in potential energy gravitation only depends on how much your elevation changes, how much further you are from the center of the earth. And so that's going to be the 3 meters, and that's going to be a positive 300 joules. And you would expect that to be a positive change because you're getting further away from the center of the earth. Well, now, part C is asking for the change in kinetic energy. This is another one of those cases where we don't know how fast it was going to begin with when we started looking, and we don't know how fast it's going when it ends. And we don't care. We just want to know how much it changed during the pull. Now, if I go up to this equation here, the Verk external is equal to the change in kinetic energy plus the change in gravitational energy. The Verk, we said, was a positive 275 joules. And the change in gravitational potential energy was a positive 300 joules. Well, what do I have to add to a positive 300 to get a positive 275? Well, change in kinetic energy better be negative, okay? It better be equal to a negative 25 joules. And that means that this block slows down as it goes up that ramp. You're not pulling hard enough to speed it up. You're not even pulling hard enough to make it go at constant speed. And that's why it's dangerous to assume that all problems start from rest. This block clearly could not have been stopped when we started pulling, because you can't slow down from stopped. That's just one of the things you learn in driver's ed, okay? So that's how we do those types of problems. They aren't very common, but they'll probably show up on the exam. I think you can count on it. Now we're gonna go a different direction. We're gonna look at that problem from chapter 8 on momentum. And I worked this problem in the lecture for today on Friday, the 27th of March, but I'll work it here as well. We have a brick wall, and we have a ball that is coming into that brick wall, and it initially is moving at 15 meters per second to the left. And then it bounces with a velocity of 10 meters per second to the right. And we're told two things. We're told that the mass of that ball is 200 grams or 0.2 kilograms. We always put our mass in kilograms. And we're also told, excuse me, that the time for the collision is 0.02 seconds. And what we're asked to find is the average force over that collision time. Now, what we learned last day in lecture on Wednesday was that the grand high equation of chapter 8, the one equation to rule them all, was that the average force times the time that that force acts is what changes the momentum, okay? This we call the impulse, and this would be the change in momentum. Okay? Now, remember, momentum is defined as the mass times the velocity. Okay? It's a vector quantity. And so if I want to find the average force, and I know what the time is, I better be finding the change in momentum. Well, whenever I want to find the change between two vectors, I put them tail to tail. Now my initial vector is going to be 0.2 kilograms times 15 meters per second, okay? And that's going to equal 3. Well, 3 what? Well, 3 kilogram meter per second. Well, what is that combination of units? What do we call that? And as you saw in the lecture, there's just no name that's been given to that. And so I'm going to call it in this class the Franci, okay? The Francis. So this, I've got 3 Franci spelled like that. Now, the final momentum is going to be 0.2 kilograms times 10 meters per second to the right, and that's going to be 2 Franci. Now, you're tempted to say, well, what's the difference between 3 and 2? Well, that's just 1. 3 minus 2 is 1. But these are vectors, and you're not taking the difference between 3 and 2. You're taking the difference between 3 to the left and 2 to the right. And when you want to find the difference between vectors, you put them tail to tail, and then you ask, what vector do I have to add to my initial to bring it all the way down to 0 and out the other way to turn it into the final? So that change of momentum is going to be 5 Franci to the right. Now, if you aren't comfortable with vectors, if vectors are not your friend, then just use what we call the math. If we call to the right the positive x direction and to the left the negative x direction, then the change in momentum is going to be P final minus P initial. Well, P final is to the right. That's 2 Franci to the right, so it's positive. And then I have to subtract the initial. The initial is 3 Franci to the left, and to the left is negative. And if I subtract a negative, that's adding. So that's going to give me a positive 5 Franci. So whichever way you want to do that is fine. At the end of the day, we have this equation here. The average force is going to be, times the time. Well, let's put the time in there. Times 0.02 seconds is going to equal the change of momentum, which is 5 Franci to the right. And that means that the force is going to be 5 Franci to the right divided by 0.02 seconds, and that's going to be 250 newtons to the right. So on average, this wall is pushing on the ball to the right, which makes sense because that's the direction the ball changed, with an average force of 250 newtons. And that's all there is. Thanks for joining us today. And now a word from our sponsors.